Question 17C. Two charged particles A and B carry a charge of positive 2q and negative q respectively. First part of the question is asking us, what is the electric potential V at a distance x from the origin on the x-axis? So here in the question you have two charged particles A and B. Charge on A, which we will write as QA, is positive 2q, and charge on B, which we will write as QB, is negative q. And we need to find what is electric potential at a distance x along the x-axis. And this point where we are finding potential, we will call it as P. We know that electric potential is a scalar quantity. So if I have to find potential at point P because of two charges, I will write V to be equal to potential due to charge A plus potential due to charge P. That gives me VA we can write as KQA over RA, where RA is the distance between charged particle A and point B. So this is RA. And VB we can write as KQB over RB, where RB is the distance between charged particle B and point B. Now we can see from the figure that I can find RA and RB using Pythagorean theorem. So we write RA to be equal to square root L squared plus x squared, which is the same as the distance RB, since both particle A and particle B are equidistant from point B. So if we substitute the values here, we can write K is common in both the terms, so we can take it outside of the bracket. RA and RB are both equal to square root L squared plus x squared, so I can take that also out of the bracket. Square root L squared plus x squared. And then we are left with charge of particle A plus charge of particle B. Now substitute the values of Q. K over square root L squared plus x squared. QA is positive 2Q and QB is negative Q. And when you solve this, you get potential at point B to be equal to KQ over square root L squared plus x squared. So this is potential at point P, which is a distance x on the x-axis because of charged particle A and B. Part 2 of the question. A third charged particle C carrying a charge of positive Q is placed at x equals 0. Calculate the potential energy in the system given that L equals 0.2 meter and Q equals 12 nanocoulomb. So here we have the charge Q to be equals to 12 nanocoulomb, which is 12 times 10 to the power negative 9 coulomb. QA is positive 2Q, QB is negative Q, and QC is positive Q. The distance L is 0.2 meter, and we need to find the potential energy of the system. Potential energy of the system is nothing but the work done in assembling each of these charges in the given configuration. So if I can find the work done in bringing each of this charge to their given position and add them together, we will find the total potential energy of the system. So let's start with an empty space. First, we bring charge particle A from infinity to its position here. Particle A has no other charges to interact with when it is placed in its position. So work done in bringing particle A is equal to 0. Then we bring particle B from infinity to its position. B can interact with the charge of A, and we have to do work against this interaction to keep B in its position. So work done in bringing particle B will be equal to KQA QB over RAB, where RAB is the distance between particle A and B, which from the figure you can see is 2 times L. So we substitute KQA is positive 2Q QB is negative Q, RAB is 2 times L. So work done in bringing particle B is negative KQ squared over L. After this, we bring particle C from infinity to its position here at the origin. When particle C is brought here, it can interact with particle A and B, and we have to do work against this interaction to keep C at its position. So we get work done in bringing particle C to be equal to KQA/QC over RAC plus KQB/QC over RBC, where RAC is the distance between charged particle A and C, which is L, and RBC is the distance between C and B, which is also L. So let's take the common terms out here. K and QC are present in both terms, so we will keep it outside. RAC and RBC are both equal to L. Then QA plus QB. Now let's substitute. QC is just Q over L. QA is positive 2Q. QB is negative Q. And when you solve this, work done in bringing particle C will be equal to positive KQ squared over L. Then potential energy of the system is nothing but the work done in bringing all of these charges. So we can find potential energy of the system by adding work done in bringing particle A plus work done in bringing particle B plus work done in bringing particle C, all from infinity to their position here. That is equal to 0 plus negative KQ squared over L plus KQ squared over L. That gives me the potential energy of the system to be equal to 0. In part 3, we have to determine the work done by the electric force when C is brought from infinity to the origin. So here particle C is brought from infinity to origin, and when it is brought at its position, it can interact with particle A and B, and we have to do work against this interaction to keep particle C fixed at its position. So work done in bringing particle C will be equal to KQA/QC over RAC plus KQB/QC over RBC, where QA here is given as positive 2Q, QB is negative Q, and QC is positive Q. RAC is the distance between charge A and C, and we know from the figure it is equal to L. RBC is the distance between charge B and C, which is also equal to L, and L is given as 0.2 meter. Now let's take the common terms outside. K, QC are present in both terms here. RAC and RBC both are equal to L, QA plus QB. Now substitute the values of Q. QC is positive Q, QA is positive 2Q, QB is negative Q. So that gives me the work done in bringing the charge particle C is equal to positive KQ squared over L. If we substitute the values of K, Q, and L, we get K is 9 times 10 to the power 9. Q here is 12 nanocoulomb, which is equivalent to 12 times 10 to the power negative 9 coulomb. So 12 times 10 to the power negative 9 squared over 0.2. That gives you the work done to be equal to 6.48 times 10 to the power negative 6 joule, or you can write this as 6.48 microjoule.